Welcome, my name is Kevin Knable, and I'm with the University of Texas San Antonio, and today I'll be discussing my research on core shell quantum dots, specifically cadmium and lead-free core shell quantum dots. So first, I want to define what is a quantum dot and what can you use it for. So a quantum dot can essentially take UV light or high energy light and convert it into a lower energy light. So I give an example of that here with our quantum dots, where we're exciting them under 365 nanometers, and they're emitting in the red around 650 nanometers. A little fun fact about a quantum dot is, depending on the size of the quantum dot, depends on what color it'll emit. So a large quantum dot will appear to be more red, whereas a smaller quantum dot will appear to be more blue. What's interesting about a core quantum dot specifically is depending on the composition of materials that you're using, the size of the shell and the size of the core depends on what charge carrier behaviors you have. So you can have a type 1 charge carrier behavior where all your charge carriers are located in the core, or you could have a type 2 quantum dot where one type of charge carrier is located in the core and the other type of charge carrier is located in the shell. That being said, quantum dots can be used in the photovoltaic industry for things like solar cells, LED displays, and things like that. That being said, depending on what your application is, a type 1 particle may be more desirable for you, or a type 2 particle may be more desirable for you. But the main problem is most of the studies on core shell quantum dots have been done on cadmium and lead-based quantum dots. And that is a problem because cadmium and lead are known to be highly carcinogenic. So what we propose instead is to use copper and indium. For a quick overview of the poster, we'll be beginning by discussing how we synthesize these particles. I'll be discussing a composition experiment that we performed on the core where we changed the copper to indium ratios. I'll just be discussing how does the zinc shell affect the photoluminescence of our particles. We will be talking about the lifetime decay of the core versus the core shell. And we will also be discussing our study on the absorption spectra data utilizing Stokes and Jolensky's method, and some early indications that we may have a type 2 particle after we add the shell. However, more studies need to be done to confirm that behavior. So we synthesize these particles by making two precursor solution. We make one precursor solution of copper 2 chloride mixed with MPa, and we adjust it to pH 9. We make another precursor solution using indium 3 chloride mixed with the MPa, and essentially what we do is we add both precursors together at the same time and we stir for 5 minutes. Next, we'll add sodium sulfite hydrate. We'll heat our pot up to 90 degrees Celsius for 30 minutes. Then we will add zinc acetate if we would like to add a zinc shell, and we'll let it stir for 5 more minutes just to allow for the shell to grow. After that, then we'll cool down to room temperature. So we performed a ratio study on these quantum dots, and we were synthesizing these from a 1 to 4 copper to indium ratio all the way up to a 1 to 8 copper indium ratio. And what we observed is as you go from indium poor to indium rich synthesis, that there's this minor blue shift in your spectrum. Now we observed this in the core of the particle, so the particle that doesn't have a shell, and we observed this in the particles with the shell. So as you increase the indium content, you see this blue shift. Another thing I would like to point out is that if you would like to use these for like silicon solar cells, their emission range is in the perfect area for the absorption for silicon, and it doesn't change too much, so all these particles would be ideal for using that for those purposes. Another thing that I would like to point out is that as you add the zinc shell, you get this enhancement in your photoluminescent spectra. So you can see that when we add the zinc shell, that our photoluminescence increased by 387%, or the integrated area increased by that much. So the next thing we decided to look at was what is the optimal ratio to synthesize these with to give you the best photoluminescence. So you might be interested in this for like applying them to solar cell or LEDs, so this is something that you may want to know. And what we discovered was that if you synthesize these at a 1:6 ratio, you get the best photoluminescence properties. And our peak was observed to be 650 nanometers for our experimental conditions. And you can see that the integrated area for the 1:6 ratio is the highest, but as you increase the ratios, your photoluminescence will start going down. The next thing that we decided to do was take the lifetime measurement, and in red is the lifetime measurement of the core, and in blue is the lifetime measurement of the core shell particles. So next we decided to perform a Taux plot and Yadolinski's plot on our absorption spectra data. If you're not familiar with Yadolinski's method, the derivations for it is down here. This is the equation you typically see when you perform a Taux plot. Yadolinski takes this equation, he performs a natural log on it, takes a derivative, and then takes the inverse of that. And this method is also referred to as the inverse logarithmic differential method, or ILD for short. So when you're doing an ILD plot, the ILD method, or Yadolinski's plot, will give you a little bit more information than Taux will. So if you remember in Taux, you typically know what type of material you're working with, like whether it's direct or indirect. So you have to assume this M value. Well, Yadolinski's method doesn't require you to assume this M value. It gives you the opportunity to find that M value. So based off that, we looked at this plot here for the core of our particles, and we saw that our slope was the M value based off our slope was 0.7, which is fairly close to the 0.5 value for a direct material. So this was an indication that our quantum dots were behaving like a direct material just with the core. Now something interesting happened when we put the addition of the shell. Yadolinski's method suggested that now our material is now behaving more as an indirect material because this M value changed to a 2. So we decided to do the corresponding Taux plot assuming that it's indirect. We decided to look at our estimated band gaps and compare these two methods together, and we saw that we always had a percent difference under 10%. So for the core, our percent difference was 6.8, and then for the core shell, the estimated value percent difference was 2.1. To summarize our poster, we demonstrated that there is a degree of tunability by controlling the composition of your particles as related to the emission spectra. We demonstrated that if you synthesize with the indium-rich synthesis, that your particles will appear to be more blue. And if you synthesize with the indium-deficient synthesis or indium-poor synthesis, they will emit more in the red color. However, this degree of tunability is relatively small, within a few nanometers of themselves. So in general, these particles will emit around 650 nanometers. We demonstrated that there is a enhancement in your photoluminescent spectra just by adding the zinc shell. We showed that there is an optimal ratio to synthesize these with, and from our experiments under our experimental conditions, the 1:6 ratio was the optimal ratio to synthesize these that gave us the best photoluminescence. We then decided to take the lifetime decay measurements for the core and core shell. Then we investigated the absorption spectrum using Taux and Yadolinski's method, and from this we were looking at the 1:6 ratio sample, and we saw that the core, according to this analysis, appears to be behaving as a direct material, whereas when we add the addition to the shell, or when we add the shell to the core, it then appeared to be behaving as a indirect material. Now this may be an early indication for this sample that it is behaving as a type 2 type particle. However, more research needs to be done to confirm this behavior and this information. That being said, I would like to thank you for taking the time to listen to my presentation. If you have any questions, feel free to send me an email or a message in the app. I would also like to thank the University of Texas Graduate School and the Department of Physics for the financial support of this project. Thank you and have a wonderful day.